Here's a swimming problem. A swimming pool has a length of 50 meters and a width of 30 meters. Its cross-section is given below in the picture. The pool is filled with water at a rate of 25 cubic meters per minute. How fast is the water level rising at the deep end when the water depth is 3 meters there? And what about 5.5 meters there? Let's consider 3 meters first. Step 1 is to draw a picture. That's already been done for us in this case. So we'll move on to step 2, which is write an equation. We need an equation for the volume of water in the pool, and we need this equation to be valid when the depth at the deep end is 3 meters. So this is the deep end over here. We know that the whole length is 6 meters. And so when the depth is 3 meters, I'm somewhere in this triangular section, right? This is 1 meter. And so then this distance is 5 meters, right? And then the entire length of the pool is 50 meters, and this sort of shallow part here is 10 meters. So this length is 40 meters of this dotted line, right? So the water is somewhere in here, which means that the volume of the water is equal to the area of the cross-section, which in this case is a triangle, times the width of the pool. So the volume is equal to the area of this cross-section. We'll call this little height h, and maybe we'll call this variable w for water. So the volume is area of the cross-section, which is 1/2 of h times w. It's this triangular section here. And then we'll multiply by the width of the pool, which the problem gives us as 30 meters. All right, well, I have too many variables here, so I need to eliminate one of them. I know how much the volume is changing, and I really want to find out how fast the water level is rising. So the variable that I want to keep in there is the h, which means I need to get rid of my w, right? So I notice that I have similar triangles. One of my triangles is here, and my other triangle is here, right? Two right triangles sitting inside each other like that always gives me similar triangles. So the ratio of their sides is equal, which means that 40 over 5 is equal to, it's the side here and the side here, w over h, corresponding side here and here. Well, 40 over 5 is equal to 8. So I have 8 is equal to w over h. Multiplying both sides by h, I get 8h is equal to w. So now I can substitute that in my equation, which means that the volume is equal to 1/2 h times w, which is 8h, times 30. So simplifying still, I have 1/2 times 8, which is 4h squared, times 30, and 4 times 30 is 120h squared. Step 3 is to differentiate. We differentiate both sides of this equation, remembering that both v and h are functions of time. So I have differentiating the left-hand side, dv dt, equals 120, using the chain rule, 2h dh dt. Finally, let's solve the problem. Finally, I solve for dh dt, which is the change in the height that I'm looking for. So I know that dv dt from the original problem, the pool is filled with water at a rate of 25 cubic meters per minute. So dv dt is 25. 120 times 2h. So in this case, when the water is 3 meters, so h is 3 times dh dt. So in this case, I get 25 equals 720 dh dt. And so dh dt is equal to 25 over 720 meters per minute. Let's solve the problem again, except this time, let's use the height of 5.5 meters instead of 3 meters. Now I need a formula for the volume of the water when the water level is at 5.5 feet. So 5.5 feet is somewhere up here. So the water level is now way up here. So the volume, again, is the area of the cross section times the width of the pool. The width of the pool is still 30 meters, but the area of the cross section is a little bit different in this case. When I'm above 5 meters, I have the whole triangular section filled. So the area of the triangle section, that's here, right? Well, this is a right triangle, so it has height of 5 meters and length of 40 meters. So its area is 1/2 times 5 times 40 meters, or 100 square meters. I also need to add on, so I add on the area of the rectangle piece. The length of the rectangle piece is 50 meters. And the depth of the rectangle piece here, my h tells me how deep the pool is. So this is really h minus 5. I take away these 5 meters that I already accounted for, and then I am looking for how much above 5 meters that is, because that's when the water starts coming over this part here. So in the case where h is equal to 5.5 meters, then h minus 5 is 0.5, and that is how far above the triangle section that we are. So then the area of the cross section volume is equal to 100 plus 50 times h minus 5 times the 30 meters, which is the width of the pool. So let's go ahead and simplify this a little bit. So volume in this case is 100 plus 50h minus 250 times 30, or 50h minus 150 times 30, or 1500h minus 4500. So this is my volume function. You notice that I only have one variable here, which kind of makes sense because I don't have this width that's changing all the time anymore since I'm above that triangular section. So I take the derivative of both sides. dv dt is equal to, well, 1500 dh dt minus the derivative of 4500 is just 0. So now I know from the problem that dv dt is still 25 cubic meters per second. So 25 is equal to 1500 dh dt. So that means that dh dt is equal to 25 over 1500 meters per minute. Okay, so I maybe noticed that when I took the derivative, I didn't have any h's anymore, and so this dh dt doesn't actually depend on the height. Well, that makes sense if I come back and look at the picture. As I'm filling this triangular section, it's filling really fast at first and sort of slows down as the water gets deeper since I'm moving through this triangular section. But once the triangular section is full, I'm just pouring water into this rectangular region, and so the height, where I am on the height, as long as I'm more than 5 meters, the rate at which the rectangular section is filling is not changing, right? So we got two different answers to two different problems here, and both of them make sense. Great. Keep practicing your related rate problems, and good luck.